the moon has always been our loyal neighbor, stabilizing Earth's axis and influencing our tides. But what if the moon's orbit was disrupted and it was sent hurtling toward us? How much time would we have before impact, and what kind of destruction would such a collision unleash? Could modern technology offer any solutions? Or would we be helpless against this cosmic disaster? In today's episode of TM What If, we'll break down the science of orbital mechanics, the physics of planetary impacts, and explore the terrifying possibilities of an Earth-Moon collision. Get ready for a mind-blowing journey into the ultimate astronomical disaster. How could the moon crash into Earth? According to the movie's official IMDb entry, a mysterious force knocks the moon from its orbit, causing it to plunge toward Earth. That's not a lot of information. Is there really a way to make that happen? Let's start with a basic model of how the planet and its satellite interact. A gravitational force pulls Earth and the moon toward each other. This force depends on the mass of both objects and is inversely proportional to the square of the distance between the centers of the two bodies. You might think that this gravitational force would be enough to make the moon crash into the Earth, and that would be true if the moon weren't in orbit around Earth. However, since the moon is moving in a direction that's perpendicular to the gravitational force, this force causes its path to curve, making it loop around the planet instead of diving into it. Forces cause a change in momentum, where momentum is the product of an object's mass and velocity. Since velocity is a vector, the momentum value depends on the direction in which the object is moving. If a force acts on an object in a direction perpendicular to its momentum, the object will move in a circle with the force pointing toward the center. This is why the moon moves in a circular orbit. A sideways force due to its gravitational interaction with Earth pulls it toward the center. But wait, if Earth pulls on the moon to make it move in a circle, wouldn't the moon pull back and make Earth move in a circle as well? Yes. Both bodies interact and orbit around a common center of mass. You can think of the center of mass as a balance point for everyday objects. For the Earth-Moon system, this center of mass is much closer to Earth since its mass is significantly larger than that of the moon. Naturally, Earth's motion is much smaller than the moon's, but here's why. There's only one gravitational interaction between Earth and the moon, meaning the magnitude of the force that the moon exerts on Earth is the same as the force Earth exerts on the moon. Both should experience the same change in momentum since they are subject to the same force. However, because Earth's mass is 81 times greater than the moon's, it will have a smaller change in velocity. This means the size of its circular orbit will be much smaller. In fact, the orbital radius of Earth is smaller than the planet itself, which means the center of mass of the planet moves in a circle that is smaller than the planet. Ultimately, this appears as a slight wobble. Now, I'm going to use this basic introduction to orbital mechanics to build a model of the Earth-Moon system in Python, so we can observe what happens when some mysterious force pushes on the moon. If you find this look strange, it's because it accurately represents the Earth-Moon distance. Many illustrations make both bodies appear much larger for visual appeal. I'm choosing not to do that because I want to be honest with you rather than mislead you. I hope you understand that this isn't running at the real speed. If it were, the moon would take 28 days to complete one orbit, which would be too dull to watch. Notice that the Earth does indeed orbit in a circular path. Now, let's start experimenting. We'll begin by pushing the moon toward the Earth using a force that's 50 times stronger than Earth's gravitational pull, applied for 1 hour. We need a force significant enough to produce visible effects, but the duration should be short enough so we don't have to adjust the force's direction as the moon moves. This simulation continues for about 8 months after the initial 1-hour push. Even after all that time, you'll notice that the moon hasn't crashed into the planet. The push only shifted it into an elliptical orbit. Since the mysterious push was directed through the center of mass of the Earth-Moon system, it didn't alter the system's angular momentum. Angular momentum is a measure of rotational motion dependent on mass, velocity, and position. The moon's angular momentum remains constant, so as it gets closer to Earth, its orbital speed must increase. However, because it's moving faster sideways in its orbit, this increased speed causes it to simply zip past Earth without colliding. Additionally, the Earth-Moon system is now moving to the left. This is because the push applied an external force that shifted the total momentum to the left. This shift would cause Earth to adjust its orbit around the Sun, but the change would be minimal, so there's no need to be concerned about it. Let's focus on the Moon instead. In fact, let's try another push. We'll apply the same amount of force for the same 1-hour duration, but this time, instead of pushing towards Earth, we'll push in the direction opposite to the Moon's motion. Here's what happens. With a push in the opposite direction, the angular momentum decreases. This results in a reduced overall rotational speed. The Moon doesn't stop orbiting entirely, but it now orbits slowly enough that it behaves more like a rock falling towards Earth, coming close to a collision. The most effective way to make the Earth and the Moon collide would be to completely freeze the Moon's orbit, which in physics terms means reducing the Moon's velocity to 0 relative to Earth. Once the Moon stops orbiting, it would fall directly into the planet due to Earth's gravitational pull, causing it to accelerate as it approaches. This scenario is similar to dropping a rock on Earth, except on a much larger scale, which would make it an epic, movie-worthy event. To achieve this, you would need either a much greater, mysterious force or a prolonged push. Could the Moon pull away Earth's oceans? A collision isn't the only way the Moon could devastate us. In one scene from the trailer, it appears the Moon is so close that its gravitational pull draws the ocean away from the Earth's surface. Could that actually occur? Now imagine placing a 1-kilogram ball of water on the Earth's surface. This water has mass and experiences a gravitational attraction towards the center of Earth. At the same time, the Moon exerts a gravitational force pulling in the opposite direction. Which force would be greater? We can calculate both forces using the universal gravitational force formula. For the interaction with Earth, we'll use Earth's mass and the mass of the water. I chose 1 kilos for simplicity. The distance r here will be from the center of Earth to its surface, which is just the Earth's radius. For the Moon's interaction, we'll use the Moon's mass and the distance from the Moon's surface to the water, plus a small additional distance since they aren't actually touching. You can observe that the gravitational force from Earth is significantly stronger than the force from the Moon. If this were a tug of war, Earth would definitely win, and the ocean wouldn't budge. However, what if the Earth-Moon system isn't stationary but rather in a close orbit, both moving along a circular path around a common center of mass? If the bodies are in motion, it implies that the water is also moving since the Earth-Moon system would be orbiting in a circle. For the water to remain on Earth, the total force, the sum of the gravitational forces from both Earth and the Moon, must be equal to the force required to keep that water moving in a circle. Instead of causing the water to circulate in a circle, I can use Earth's reference frame and introduce a centrifugal force. This force is necessary in an accelerating reference frame to ensure that normal physics principles apply. Here's a more detailed explanation. If the Moon were extremely close to Earth, and both were orbiting a common center of mass in a perfect circle, they would complete an orbit in just 2.3 hours, instead of the usual 28 days. In this scenario, the water on Earth's surface facing the Moon would experience a centrifugal force of 3.55 newtons, pushing it away from the Moon. However, the gravitational forces from both Earth and the Moon would pull pull the water back toward Earth with a combined force of 5.48 newtons. Therefore, even in this unusual orbital setup, the water would still be drawn more strongly toward Earth than toward the Moon. Essentially, this is an exaggerated form of ocean tides. Tides result from the interaction of three forces: Earth's gravitational pull, the Moon's gravitational force, and the centrifugal force from Earth's rotation as the Moon exerts its pull. However, since different areas of the Earth's surface are at varying distances from the Moon, the combined forces cause the water to bulge in two locations, one on the side of the planet closest to the Moon and one on the opposite side. In conclusion, from a scientific perspective, having the Moon this close would be disastrous. The Moon would break into pieces as soon as it reached the Roche limit. The Moon itself would disintegrate before it could ever reach Earth's surface, which would be quite a spectacle. But what exactly is the Roche limit? In celestial mechanics, it's the distance at which the gravitational force keeping a satellite intact is overcome by the tidal forces trying to pull it apart. To put it simply, the Moon can only approach to within 18,170 kilometers, 11,170 miles of Earth, before, boom, the tidal forces would tear it apart. All the footprints and flags we've left on the Moon, along with its craters and valleys, would spread out to create a stunning ring of debris around Earth's equator. This would make Earth the second planet in the solar system, after Saturn, to have such a magnificent ring. However, this spectacle wouldn't last long, as the fragments of our former satellite, the Moon, would eventually rain down on Earth. It would be as if hundreds of thousands of asteroids were raining down on us, obliterating entire cities in the process. As the Moon began its journey towards Earth, its tidal effects would become increasingly intense. By the time it reached the Roche limit, it would generate tides as high as 7,600 meters, 30,000 feet. Our planet would be ravaged by a relentless barrage of tsunamis, 10 times a day. For a brief period, hardcore surfers might find joy in riding some epic waves. On the flip side, this could offer a remedy for global warming. With the Moon moving closer, Earth's rotation would accelerate, leading to shorter days and cooler global temperatures, which would alleviate concerns about climate change. Unless, of course, asteroids incinerated the Earth. In that case, there would be no one left to worry about anything. Personally, I wouldn't be concerned anyway, as the Moon is actually drifting away from us at a rate of 4 centimeter, 1.5 inches per year. So it's highly unlikely we'll ever see those beautiful Saturn-like rings around Earth.